Welcome to the online interview of Professor Dibyendu Chakrabarty regarding the latest Indian solar mission, ADITYA-L1. And I just want to make a brief introduction, though it is not required for Professor Chakrabarty, that he is a PI of the ADITYA-L1 ASPEX onboard experiment. And he is a professor in Physical Research Laboratory, Ahmedabad. So welcome, Professor Chakrabarty, for giving us your precious time for making this interview. And we thank from the perspective of this entire mission and your contribution to the science, and of course from the point of view of the IASES. On behalf of IASES, I welcome you for this interview. This is the first questions from my end that we know it is everyone knows about the naming of Aditya, that is the name of sun, and of course it is the first mission, the first solar mission of India. But this mission is incomplete without the part of L1. It is connected, the complete name is ADITYA-L1. So the first question from my end, that if you please give some elaborate discussions on this matter of this ADITYA-L1 and what is the implication and what is the importance of this L1 terminology in this entire mission.
Yeah, thank you. First of all, Sudipto and Ankan. This is a great occasion because we are standing at a juncture of having ADITYA-L1 mission. Now you already know the date is going to be launched on Saturday, the 2nd of September at 11:50. That's the launch time. And this is, in a nation's history, I think you don't see many occasions when a moon mission and the solar mission are happening at the same time, almost at the same time, separated by around 10 to 12 days. So it's a very special inflection point in the history of space science in India. Now, to come to your question that why L1, before I explain this, we have to understand that we do know that we are in a planetary system. We live on a planet, and there are several planets, and the Earth, and our star is the sun. And if you take a Earth and the sun, it's a two-body system. And if you want to place a satellite in between these two bodies, and if you want that satellite to be in a stable orbit, it becomes a kind of a three-body problem. But you can reduce the problem. In a three-body problem, it's very difficult to make an analytical solution and find out an orbit which is stable. But suppose under certain conditions, when the satellite moves in a third body moves in a particular orbit where the gravitational pull between the two bodies balances out each other and also the centrifugal force of that body when it is moving around that point, that helps. That gravitational pull and the centrifugal force, they actually balance out each other. Then it helps that the third body to move in an orbit which is stable. In other words, you can consider a gravitational potential. For example, in a two-body system, the sun has gravity and the Earth has a gravity because they are massive bodies. And sun is more massive than the Earth. So sun can distort the gravitational potential in a much more significant manner than the Earth. Now, if you put a satellite, then it will have to move in this gravitational potential. In this kind of three-body problem, you can find 5 positions, which was pointed by almost in 1722, if I remember, by scientist Lagrange, and he actually found out that if you make certain approximation, then you can solve this reduced three-body problem to reduce into to find out the trajectory of that third body, and you can define 5 positions in space where the third body can move in a stable orbit. These are called Lagrange points. In other words, if you can put it, when a body is around the Lagrange point, the gravitational pull between Earth and the Sun in these two body system will play out in such a way that you will be able to attain a stable orbit at that point of time. So there are such 5 points. And because we call it a Lagrange point, so L stands for the Lagrange point. And there are 5 such points. Now, ADITYA-L1 is associated with the first Lagrange point, which is between the Earth and the Sun. And the other 4 Lagrange points, one is behind the Earth, one is behind the Sun, and the other 2 is at 60 degrees with the Sun-Earth line. One is ahead of the Earth and another is behind the Earth. So these are the first 5 Lagrange points. So 60 degrees ahead of the Earth is the L4 point, and 60 degrees behind the Earth is the L5 point. And L2 point is where the James Webb Space Telescope is there, because you know that that telescope has to look at the deep space for astronomical observation. So it has to look opposite to the Sun so that it can actually gather those lights which are very, very faint and coming from the early universes. So it's very logical that you put an astronomical telescope at L2 point looking at the deep space. L1 point, if you want to observe the Sun, I will come what are the advantages of the L1, putting a satellite at the L1 point. But if you want to observe the Sun, then L1 point is one of the strategically good location. And L3 point is very difficult to access, which is because it is behind the Sun. It's very difficult to access it. And even if you access it, it will be difficult to send even if you make observation, you have to send the data back to Earth, which will be very difficult because Sun is also a radio source. And also because you are behind the Sun, your line of sight requirement will not be satisfied. L4 and L5 have certain advantages too. And so if you look at L1 point now, it has 3 advantages. One is that if you put in an orbit around the L1 point, which we call halo orbit is a big orbit. You see, you don't put a satellite in a point because that point, even if equilibrium point, even if there is a perturbation in the gravitational potential, that point will be pulled towards a massive body. It depends. So therefore, if you have to put a satellite at the Lagrange point, you have to put it in an orbit. And that orbit is a very large orbit. The dimension of it is around, let us say, is very large. So, for example, a typical dimension, if I can give you, in the x direction is around 208,000 kilometers, 208,000 kilometers. In the y direction, which is sort of dawn dusk direction of the Earth, which is around 670,000 kilometers, and in the z direction, which is the north-south direction, which is around 120,000 kilometers. So you can see it's a very large orbit in which the satellite moves around the L1 point. Now, this orbit is slightly inclined because if this orbit is in the plane of the Sun and the Earth, then it will be very difficult to communicate with the Earth because Sun is a radio source and you have to communicate through radio signal from that point, from that satellite to Earth. And there will be radio interference. So as a result of which you actually tilt that satellite orbit, halo orbit, in a certain angle so that your communication from that satellite to the Earth, because whatever measurement you are doing, you have to send back to Earth. And it should not get disturbed by the radio interference because Sun itself is a radio source. And in order to avoid that, you tilt that angle a little bit so that this problem is averted. And therefore, at Lagrange 1 point, you put it in an orbit, which we call halo orbit. And in that orbit, you would put that satellite. It should look at the Sun, and there won't be any eclipse whatsoever. Because in any earthbound orbit, always looking at the Sun may not be possible because it is not, there will be certain geometry where there will be Earth coming in between the satellite and the Earth and the Sun. So the first, to make the long story short, the first Lagrange point is a place where solar observation is very much suitable because you can have 24/7 observation of the Sun, and there are other 2 advantages as well. Because So I'll come to these advantages a little later, but to answer your question, this is the first Lagrange point of the Sun-Earth system, where the gravity of the Sun and the Earth balances out. You put it in an orbit. It has the capacity to enable you to look at the Sun 24/7, and it is 100 times of the distance between the Earth and the Sun, which is, in technical language, we call it as 1 astronomical unit. And this distance, if I have to spell out the absolute number, is around 1.5 million kilometers, whereas, as you know, the distance between the Earth and the Sun is 150 million kilometers. So therefore, the ADITYA-L1 satellite is actually placed at a halo orbit. So this will be placed at the L1 point. So this is why this mission is called the ADITYA-L1 mission. ADITYA is Sun, and a mission dedicated to observe the Sun in totality is naturally named as ADITYA-L1 observatory or satellite.
Absolutely. Very interesting in terms of this two-body rotational problem kind of thing. Now, the next question can be asked by Dr. Das.
Thank you, Professor Chakrabarty. It is nice to hear about the proposed launching period and the position in space. As you have just mentioned that the Earth to Sun distance is roughly 1 astronomical unit, this is roughly 150 million kilometers. Then what is the advantage of just advancing 1.5 million kilometers from the Earth to observe it from the L1 point? This is the first question. And my second question is that I can understand that the much radiation would be blocked due to the Earth's atmosphere, but it could be observed from the low Earth orbit, which is just 2,000 kilometers away from Earth, actually. And we heard that this mission actually planned long back, roughly 15 years back, and it was proposed to sending in the low Earth orbit. So why has it been changed?
Yeah, so I'll break your question into two parts. The first reason that why we are sending it to L1 point, and the advantage of L1 point for solar observation is threefold. The first reason is that you can observe the Sun 24/7 without any eclipse happening. So you can have an uninterrupted observation of the Sun. As you know that ADITYA-L1 is India's first observatory class mission dedicated to study the Sun. And therefore, if you have to maximize the observation of the Sun, you need to look at the Sun 24/7. And that is possible from L1 without any eclipse coming in between. That is one advantage of this particular point. The second advantage is that when you were at L1 point, you are actually out of the influence of the terrestrial magnetic field and terrestrial atmosphere, means Earth's atmosphere and Earth's magnetic field, which is important because when you want to study Sun, you also need to measure solar wind from a point where the satellite is located. If you are at L1 point, you are comfortably out from the influence of the Earth's magnetic field, and you have no effect whatsoever or no contamination whatsoever from the atmosphere of the Earth. So those species are not there. So you are in deep space altogether. And therefore, when you want to measure solar wind particles and solar wind magnetic field, which is there at L1 point, you are actually making sure that these measurements are not contaminated by any other thing, and you are measuring the solar wind purely, which is solar wind, and which is solar wind magnetic field. This won't be possible from a low Earth orbiting satellite, because from low Earth orbiting satellite, you can have a coronagraph, which is like blocking the solar disk and looking at the corona. That experiment is possible, and many countries are attempting that way or attempted that kind of an observation. But if you have to satisfy that you want to measure solar wind as well, you cannot satisfy this objective from a low Earth orbiting satellite, because then you are within the magnetic and influence of the Earth, and also embedded into the Earth's atmosphere. Therefore, it is to study the Sun in totality, as I said, that because to ensure that solar wind field and solar wind particles are important part to understand what's happening in the Sun, you need to go out of the Earth's influence of the magnetic field and also out of the influence of the Earth's magnetosphere. So low Earth orbiting satellite, may not be able to address all the aspects of the solar physics and solar wind physics, which is the main target of this mission, because this is rightfully termed as the observatory class mission. This is the second advantage. And the third advantage is that if you are at L1 point, if you take a normal, typical solar wind velocity, it takes almost an hour to come from L1 point to the Earth. So therefore, if you have a satellite and if you are measuring solar wind from there, you are getting 1 hour of advanced measurement. And somehow through telemetry, if you can send it back to the Earth, you are getting 1 hour forecasting capability in that process. That means you know that because the telemetry signal will come immediately, but the solar wind take almost 45 minutes to 1 hour to come to the Earth. And therefore, you have an advantage of looking at the solar wind 1 hour in advance. See, in terrestrial system, when you talk about a cyclone or a tornado, it's important that from the satellite, you know that track the location of that particular disturbances, atmospheric disturbances. And similar to that, as we are becoming a technologically developed system, we have many space assets which are hovering in space. Some are in geostationary orbit, some are in low Earth orbiting orbits. So these satellites or space assets, they are very important that we protect them from the hazards of the solar disturbances that are coming through solar wind, through coronal mass ejections, or if there is flare or energetic particles, etc. So therefore, if you can get a time of 1 hour advance warning, then it helps, because under those situations, you can't stop these events to happen, but definitely you can take precaution so that this does not damage. I will give you an example that if an astronaut is doing a spacewalk in the International Space Station, we need this kind of warning where whether it is important or whether it is advisable for the astronaut to go out. The way you give warning to the fishermen when they are going to the deep sea, you look at them and say that don't go out at this time because a cyclone is coming towards you. In the same manner, you tell the astronauts that please don't do the spacewalk at this point of time because you will be getting exposed to high energy radiation or high energy particles at that point of time. So it's very important that in the next level of technological development, when you are putting everything in space to have communication, navigation, or power lines or everything, it is important that we need to know what is happening on the sun and what is coming towards us from the sun in the form of solar wind and magnetic field in advance. So from that point of view, although this is a science mission, there is an offshoot of this mission is that we understand how to develop a forecasting system in the long run by analyzing the data for a longer period of time. And any L1 mission, which are traditionally, they survive for a long period of time because in order to rotate it in the L1 orbit, you don't require too much of fuel. And so therefore, this kind of missions, they survive for a long period of time, giving a large amount of very useful data. And that data, if you analyze it for a longer period of time, you develop the forecasting strategies and forecasting models. You will be in a position to develop those kind of models, which will give you forecasting capability the way we do it for even for lower atmospheric disturbances. So I think these advantages are there as far as L1 points are concerned. And I think this answers that why we do not put it at, why this mission was not put at, originally, this to get a little further, in 2008 when it was proposed, this was from a low Earth orbit, as you rightly pointed out. But then only one coronagraph was considered at that point of time. And coronagraph is basically you block the solar disk, which is very bright, and you look at the corona. Under normal circumstances, when you look at the sun, you don't see the corona. It's very difficult to observe the corona if the solar disk is present, which is so bright. It's like looking from a illuminated room. If you are standing there and if you want to look outside, if light is on inside the room, it will be very difficult for you to see the details, what is there in the outside. But if you switch off the light, then you can see what is the details, what is there in the outside of your room. In the same way, if you block the solar disk, you are actually blocking the brighter part of the sun and the corona, and thus enabling you to look at the corona, which contains many details. And if you want to study the corona, that is why you artificially produce an eclipse, block the solar disk in front of you, and then do spectroscopy or spectral imaging and spectropolarimetry kind of technique to look at the solar corona. And that's the whole purpose of. So if you have to have a coronographic measurement, you can of course do it from low Earth orbiting satellite as well, but you can't have all the measurements from the low Earth orbiting satellite. This is an observatory class mission, and therefore, if we have to have a holistic measurement strategies, where I'll come to that point a little bit later, that if you want to observe in multiple wavelength band, you want to observe in solar wind also, you want to measure the magnetic field as well, which is coming from the sun, all these requirements cannot get satisfied if you put it in a low Earth orbiting satellite. So therefore, it is important that if we want to study the sun in totality, we have to go at a point which enables me to do that or satisfy that objective. I hope I answered your question.
Yeah, thank you. It's nicely explained. So next, I request Dr. Sashmal to carry on.
Okay. So it was very nicely explained regarding the utilization of this L1 orbit and the comparison with the low Earth orbit satellite. Now, it is very obvious that whatever you have been discussing from the last 30 minutes or 20 minutes we are going through, that this mission contains a lot of experiments and observation, because the sun itself, not only an isolated star, though it has its own internal nucleosynthesis processes and then coming out of the plasma and then magnetic field, solar dynamo, but still it has an extended part of the solar terrestrial interaction, where the solar plasma and the solar wind and the solar photons are getting directly interacted with the planetary atmosphere. Now, definitely, it will contain a lot of payloads, a lot of instruments, and with a different objective and working principle. So, and also we know that you are the PI of this ASPEX mission, which deals with the solar wind particle experiments. So, if you please make some discussions on the payloads and its activities of this ADITYA-L1, that will be great.
So there are 7 payloads, as you know, and as I told you earlier itself, that this is an observatory class mission, and for any observatory class mission, you have to have measurement across a large electrodynamic spectrum, electromagnetic spectrum. For example, in these 7 payloads that we have, 4 experiments or payloads are remote sensing payloads, and 3 are in situ experiments or in situ payloads. Now, if you talk about the 4 remote sensing experiment, what we call remote sensing is that when you measure something, for example, you want to measure in a pond, and you can do it 2 ways. You can take a photograph, you want to detect something on the surface of the pond, you can detect something by taking a photograph, or you can actually get into the pond and then try to measure or sample or try to see what that particle is by directly measuring it. So in the first case, when you're actually making the measurement by looking at something, the light coming out from the pond, let us say, by reflection, then you are calling it a remote sensing experiment. And the second is when you are getting into it to measure, then you call it an in situ experiment. When you want to measure the solar wind, you are actually doing an in situ measurement, because you are into the solar wind and making that measurement. Or if you are measuring the solar wind magnetic field, you are into that field and making that measurement. So it's in situ experiment. So when you measure particles and magnetic field, here at L1 point, you are actually making in situ measurements. But if you want to know that what is happening in the sun, you are actually, through remote sensing measure, you are dependent on the radiations that are coming out from the sun, and different techniques you adopt to actually measure that radiation. For example, in coronagraph, when you say there are these 4 remote sensing experiment called, one of them is called VELC, or visible um, uh, emission line coronagraph. So that is the full form of VELC. It's primarily a coronagraph. So it has an occulter, so it will occult the main disk, and then you look at the corona. So, and it looks at the sun in both visible and infrared wavelength. And it makes three kinds of measurement. One is coronagraph measurement. So you look at the corona by blocking the main disk. Also, it observes visible as well as the infrared lines and does spectropolarimetry and spectroscopy. So therefore, if you look at VLC, it is looking at visible emission part of the spectra as well as the infrared part of the spectrum. Now, if you look at SOOT, which is called Solar Ultraviolet Imaging Telescope, which is SOOT, which is the second in situ experiment. VLC obviously is the biggest one. So, and SOOT comes after that. And so it is Solar Ultraviolet Imaging Telescope. And that telescope is looking at the solar near ultraviolet emission, which is between 200 to 400 nanometer in a spatially resolved manner. And as you can see, this is near ultraviolet. So one, you have covered the visible and near infrared, and here you are covering the near ultraviolet. Then you have SOLEX and Helios, which are looking at the X-ray part of the solar emission. And SOLEX is looking at the soft X-ray. That means the X-rays which are not that much energetic. And that is the SOLEX payload, which is remote sensing payload, looking at the sun as a disk and trying to detect the X-ray emission, soft X-ray emission that are coming from the sun, which is around 1 to 25 keV, looking at those X-ray emissions and trying to see that what are the changes that are taking place at the time of solar flare and other processes. Whereas Helios is meant for hard X-ray, which it will measure from 10 keV, kilo electron volt, to 150 keV. So therefore, you can see there is an overlap between SOLEX and Helios because one covers from 1 to 25 keV and Helios covers from 10 keV to 150 keV, and there is an overlap. So it's also, that means that it's through these techniques, we are not only covering a significant part of the electromagnetic spectrum, depending on the science problem, but also we are trying to look at solar wind particles and field through the in situ experiment. So, which are called ASPEX, which is actually, so let me tell you that VLC, the visible energy line coronagraph, VLC is an instrument which is coming from Indian Institute of Astrophysics. Then SOOT is coming from IUCA from Pune, and the SOLEX and Helios are coming from URSC, which is an ISRO center, URSC Satellite Center in Bangalore, and the ASPEX, which is coming from where I work, which is Physical Research Laboratory in Ahmedabad. ASPEX stands for Aditya Solar Wind Particle Experiment. So it's one of the in situ experiments which will be measuring the solar wind particles, solar wind ions, primarily protons and heliums, both at low energy as well as in high energy and in multiple directions. And then comes PAPA, which is Plasma Package Analyzer, Aditya Plasma Package Analyzer for Aditya. So that is the name, Plasma Analyzer Package for Aditya. That is the full form of PAPA. PAPA is coming from VSSC, SPL VSSC, Space Physics Laboratory in Vikram Sarabhai Space Center. And then there is one magnetometer, which is coming from LEOS in Bangalore. And so these are the 7 experiments. 4 of them are remote sensing and 3 of them are the in situ experiments. Each such experiment, each of the experiments in this mission have some uniqueness, and those uniqueness we are trying to encash in to build up a bigger picture which has not been addressed through earlier mission. You have to remember that all the earlier mission, is not that solar mission hasn't happened earlier. So there are various solar missions that has happened, but the kind of problems that we don't understand, that are too many, and each mission therefore focuses on certain scientific objectives. And ADITYA-L1 is also not an exception. So by using 7 very sophisticated instruments, we have defined certain scientific goals which we want to address, sometimes using one instrument or a couple of instruments, and sometimes using all the instruments together by combining the measurement both from remote sensing as well as in situ experiments. That is the whole idea of the observatory class mission. We want to combine various measurements to stitch the bigger picture. So it's like looking at the elephant in totality. You are not looking at the tail, or you are not looking at the legs, because you are trying to combine all kinds of measurement to find out the overall science picture that you want to address. So that's the whole purpose of this observatory class mission from India, which is ADITYA-L1.
It's a huge, and not only from the point of the scientific objective, but the involvement of the institute and the manpowers. Obviously, the most of the premier research institute in India, and also a wide group of people, I believe that they were involved and day and night round the clock for making this kind of huge project. That is, and you are absolutely correct that we are just looking for the elephant, not a small part, not a sub part of that. Starting from the sun itself to the Earth point, where the space weather can be detected from the low Earth atmosphere, especially the upper atmosphere. So I request Dr. Das to ask the next question to you.
Yeah. Thank you, Professor Chakrabarty. It's a nice explanation regarding all the mission payloads. And we have heard the names like SOHO and Parker Solar Probe among the past successful missions. SOHO was launched long ago in 1995, and it is extending its operation until 2025. And there was a Parker Solar Probe launched by NASA in 2018, and it is probably the fastest object ever built by the humans, having speed roughly 690,000 km/h. And at its closest approach, the Parker will come within the 6.2 million kilometers of the sun. So my question is that how does the ADITYA-L1 mission differ from the past mission like SOHO and Parker Solar Probe?
Yes, Ankan, and that's a very interesting question, because as you know that Parker Solar Probe has done both Parker Solar Probe, SOHO, and Solar Orbiter, the present missions. They have done remarkable job in terms of achieving the scientific goals that they have set up for themselves. For example, I'll give you an example. As you know that Parker Solar Probe is the closest now and fastest moving spacecraft that has been made or designed, and that has traveled through space at the fastest velocity, and then it has gone closest to the sun. So it's almost touched the corona of the sun, which is a remarkable achievement, because the thermal management, if you look at a spacecraft going so close to the sun and it still operates and it gives you data, that tells a lot about the technological marvel of that particular spacecraft. So it's a remarkable achievement. And Parker Solar Probe has brought out many discoveries because of the very fact that it has gone that much closer to the sun, where many things are happening. Because when solar wind is coming from the sun, by the time a lot of processes are happening closer to the sun, and if you understand those processes, it helps us to sort of understand the origin and the changes in the solar wind or in the sun in a much better way. So in that sense, Parker Solar Probe is very, very unique. If you look at the Solar Orbiter is giving you unprecedented detailed images of the sun at extreme ultraviolet and those wavelengths. So it's helping us to understand. It is also going reasonably close, not as close as Parker Solar Probe, but it's going reasonably closer. And it's giving an unprecedented detail as far as the images that it is constructing at higher energies. And therefore, this is throwing new light on how the solar magnetic fields are getting reconfigured at each moment of time. And then, as far as the magnetic field is concerned in the sun, it plays a very important role the way sun behaves, because we see all the activity cycles in the sun and in the solar particles that are coming out. they are all dependent on, in some way or the other, the magnetic activities in the sun. So it's very important to get those details, spatiotemporal details, as far as the solar magnetic fields are concerned. And solar arbiter is giving us unprecedented resolution as far as these images are concerned at extreme ultraviolet. Now, if you call up the SOHO, in fact, we are very similar to SOHO, but SOHO has a coronagraph. In fact, when the SOHO was planned, it had 3 coronagraphs, which they used to call C1, C2, and C3. The idea of this coronagraph is that they were designed in such a way they will be looking at the solar corona at different heights. So C1 was designed to look at the lowermost part of the corona. C2 is at the intermediate part of the corona, and C3 is the higher part of the corona, higher heights of the corona. Unfortunately, when SOHO was launched, the C1 didn't work. That means the observation of the closest photospheric surface, the corona, which is very close to the photosphere, those observations could not be made. Now, this is where VLC in ADITYA-L1 mission, SOHO first time brought out the different coronagraphs. So it's very unique. So similarly, all the solar mission that has happened in the past, they are unique in some way or the other. If you come to ADITYA-L1 mission, if you look at VLC, the coronagraph that we have made, it is exactly filling the gap what SOHO left. That means we are looking very close to the sun, where CMEs are actually getting formed and changing in such a way that those dynamics of CMEs are very important to predict that how CME is getting accelerated and coming out of the sun, getting created and coming out of the sun. So that means ADITYA-L1 VLC is filling the gap where information about what is happening in the corona very close to the sun is missing in great detail. In addition to that, the VLC also will be measuring the solar magnetic field more than the tens of Gausses and in the coronal magnetic field, and that will also be very important factor in addressing the coronal heating problem, which is actually, we actually know that corona is much more hotter than the sun itself, the solar surface itself. And so therefore, because magnetic field plays a very important role in releasing energy through the changes in the magnetic field, the reconnection, and then other processes, those are explosive energies that get released. And so therefore, if you measure the coronal magnetic field beyond tens of Gauss, I mean, it might help you to address the coronal heating problem in a much more better way. So these are uniqueness of the VLC payload. If you get into the SOOT payload, in one of the earlier mission, the wavelength band that SOOT is going to look at is 200 to 400 near ultraviolet emissions. In that particular band, in the previous, let us say, IRIS mission, probably, if I remember correctly, there was one small part of this band was measured by IRIS. But so far, there is no systematic attempt to measure this particular band. This band, you see, if you consider this particular band is some of SOOT, what it does, it uses 8 narrowband emission lines measurements and 3 broadband measurements. What it does, it chooses those wave emissions which are coming from different heights of the photosphere, chromosphere, and the transition region, which is connecting the chromosphere and the corona. That is where the temperature starts changing enormously in the corona. And so therefore, those emissions that are coming from different heights of the solar atmosphere, SOOT is trying to look at those emission intensity changes to understand that when a solar flare is erupting, what are the changes that are taking place? And that will enable us to understand these eruptive or explosive processes in a much better way. Eventually, all these processes are very important to evaluate space weather at Earth. So that objective you have to keep in mind. I'm talking from a at present purely from the scientific point of view. So therefore, SOOT's multi-wavelength narrowband observation in the NUV band, near ultraviolet band, 200 to 400 nanometer, is actually covering different layers of the photosphere, chromosphere, and the transition height. And if you look at now that VLC is looking at visible and near infrared, SOOT is looking at UV, and SOOT, another advantage of SOOT is, another uniqueness of SOOT is, it can spatially resolve very nicely. these emissions or the structures that are there based on these emissions. So therefore, SOOP can very well understand the flare dynamics or help us to understand the flare dynamics in a very, very unique manner. Now, these emissions are also important for ozone layers because these are the emissions in near ultraviolet. They are also part of the total solar irradiance, which is in this band, there are a lot of variabilities that are being reported. Although total solar irradiance do not vary much from cycle to cycle in a significant manner. But if you look that variation, the maximum variability comes from somewhere in this band as well. So therefore, in terms of the Earth's atmosphere and climatic impact, this emission also has it's a secondary science offshoot which people can also study using the SOOT observation. So this is a very important trade-off or spin-off of SOOT science, which is primarily dedicated to look at the solar eruptive processes like flare. And as I told you, VLC targets the CME, the coronal mass ejections that are coming, and also the temperature, the coronal heating problem. So that is the VLC's target. Now let us come to SOLEX and Helios. As I told you, SOLEX look at the soft X-ray, which is coming, and it's looking sun as a disk. So it's not resolving from where the X-ray emissions are coming, but if there is a change in the X-ray emission coming from the sun, it will be able to tell you through the spectra that which are the wavelengths that are the emission at what wavelengths it is changing. So it can actually spectrally resolve those emissions and tell you that what are the emission lines that are showing changes when these processes are taking place in the soft X-ray. And in the hard X-ray, soft X-rays, they are very important for solar flare studies, and they can be combined with SOOT measurements, which are measuring in near ultraviolet. And because conventionally when people study flare, they actually measure solar X-rays, and GOES satellite, which is at the geostationary orbit, they actually measure X-rays. Generally, solar flare intensities are classified by X-ray, and therefore X-ray measurement is very critical, and SOLEX will be measuring soft X-rays 1 to 25 keV from the L1 point, and the Helios will be measuring the hard X-ray, which is from 10 to 150 keV. Now, hard X-rays are important because while the soft X-rays are associated with thermal processes, the hard X-rays are associated with non-thermal processes. They are more impulsive. For example, I can give you an example that if you heat an object and the radiation from that object will come, and this is a thermal process because it's a direct consequence of the heating. Okay. And it's a thermal process. But in non-thermal processes, the changes are happening that is not due to the thermal processes, and you can't explain it through the thermal processes. One such example I can give you, that when you accelerate a particle to a very high velocity and you accelerate it, it actually gives off radiation. And these radiations are of very high energy. But in this process, you are not actually hitting the particle, but because it is getting accelerated, you are getting these emissions. And therefore, it's a non-thermal process. And the thermal process is where heat is directly involved. And then you are getting those emissions because there is a heating involved somewhere. And so by combining the SOLEX and Helios measurements, you get the soft X-ray as well as the hard X-ray, and there is a transition in between. And this happens during flare because there are impulsive phases of the flare that comes first and then the gradual phase of the flare. And if you want to understand flare in X-rays, you need to observe these two bands that much more critically. And you need to know that exactly where the transition between thermal and non-thermal processes are taking place. That's a very useful information, and that's a very novel observation. In terms of the novelty of these instruments is in terms of the spectral resolution of these measured instruments, they're very high compared to what is available at present. And therefore, it will help us to spectrally resolve those changes that are happening. And with that, we are expecting to do a very different science than what people have done so far. Now, let us come into the in situ experiment. ASPEX is a very unique experiment. I'm telling it not because I'm the PI of this instrument, because we have designed it very carefully by looking at the science we desire to do with this instrument. And the advantage of ASPEX is its directional ability to measure solar wind particle. ASPEX is an instrument which is not only measuring both low and high energy particles for both protons and alphas, which are the major constituents in the solar wind, but also it will be able to measure all these particles of protons and alphas in a directionally resolved manner. Okay, so both for low energy and high energy, you know that where from these particles, from which directions these particles are coming to the spacecraft. Why it is important? Because some of these particles, for example, solar wind is coming towards you primarily in a radial direction. But from solar wind, there is when solar wind gets energized, it becomes suprathermal particle, the energy of which is slightly more than the solar wind particles. And then suprathermal particle, when you accelerate them, it becomes energetic particle, even enhanced energy than the suprathermal, even more energy than the suprathermal population. And the way this transition takes place from the slow solar wind to from the solar wind to suprathermal to energetic particle, these acceleration processes are very important to know, because these energetic particles are a great threat to anything which is there in space, because these are very high energy particle. It can simply pierce through the electronics, it can simply pierce through the spacecraft if it is sufficiently energetic, and it can damage electronics. And by damaging electronics, it can cause a lot of problems, not only to the electronics of the space assets, but also by making the instruments inoperative. And sometimes it can be life-threatening as well, because if electronics do not work and if your functionality in space depend on those electronics, you are in great problem. So energetic particle measurements is very important, and it is also important to know how these particles are created from the solar wind. And also from the solar wind, it is important to know that from which direction, how it is coming towards the L1 point, so that you can evaluate the impact at the Earth very, very carefully and in very detailed manner. So directionality is a very important factor in terms of ASPEX. Now, in earlier instruments, it's not that we are doing the in situ measurement for the first time, but people have measured low energy and high energy particles from solar wind particles and also protons and alphas. But what we are doing in a very different way is to focus on the directional part of it. The whole ASPEX instrument consists of so many subsystems, and it is spread over the spacecraft. And it is looking at slow solar and the solar wind particles in 360 degree in the ecliptic plane and 360 degree perpendicular to the ecliptic plane. And the energetic particles is looking at 6 directions. One is the solar direction, another is the Parker spiral direction, which is through which the energetic particles come on most of the occasions. Then there is an intermediate channel between these two. And also it is looking at the Earth, because there is a bow shock in front of the Earth when solar wind is hitting. And bow shock is also scattering back a lot of particles towards the L1. So we also want to measure those particles. And suprathermal particles can come from any direction. So we are also having a north pointing and south pointing unit. So you see there are 6 such energetic particle units. And by having this directionality, we will be able to capture these particles coming from all the directions. And this is very important aspect. Directionality is a very big aspect for ASPEX payload. Then you come to PAPA. PAPA is actually complementing ASPEX. Some part, like PAPA, will also measure protons and alphas, or hydrogen and helium, the way which ASPEX also doing in a directionally resolved manner. PAPA will not do in a directionally resolved manner in 360 degree, but then PAPA will, the advantage or uniqueness of PAPA is, in addition to protons and alphas, it will also measure the heavier ions, which is only a minuscule in the solar wind in terms of its abundance. It's less than 1%. So PAPA is in a position, is designed in such a way to measure those, and also electrons along with it, solar wind electrons. And then there is magnetometer. You know that magnetometer is almost a mandatory instrument for any space measurement, because magnetic field, the space is pervaded by magnetic field, and solar wind is no exception. In fact, solar wind carries the magnetic field that is coming out from the sun. And therefore, because Earth is a magnetized body, how the solar wind magnetic field will interact with the Earth. And that is the subject matter of near Earth space weather. And it's very important to know that how the magnetic field in the solar wind is behaving in order to evaluate the impact of it on the Earth. So therefore, these are, as you can see, these are very unique instruments in some way or the other. They can give very good science in isolation, and they can give very good science when you combine them, either two of them or three of them or all of them. And by that will enable us to understand the processes closer to the sun as well as at the L1 point. And when you stitch them together, it can give a lot of integrated information, and we can address those processes that how CME or solar flares and how energetic particles or solar wind or how solar wind magnetic field is going to affect the Earth in the long run. So this is what the uniqueness and the purpose of these instruments. Yeah.
Thank you, Professor Chakrabarty. It's thanks for this nice explanation about the nobility of this ADITYA-L1 mission. And next, I would like to request Dr. Sashmuk to carry on.
Yeah, of course. So, as the interview is going on, and we can have the essence of this detailing about the instruments, and we know that ISRO is not recently, but slowly making a brand of making low-cost space exploration. We recently, like just the moon mission, the Chandrayaan-2, we have known for the budgetary part. It is extremely low cost in comparison to other, and there are a lot of comparison is going on regarding the Chandrayaan mission. Now, we are just coming at the end of this interview, but before we end, there are very common questions to everywhere regarding the common people, because people are highly excited about the space exploration. In the last, starting from the Chandrayaan-3 and back-to-back missions from the ISRO, and now people are also knowing about the future missions, just like Gaganyaan or just like the Gaganyaan and the Venus mission kind of thing. Now, I have two generic questions that is not very scientific. First of all, if you can give an idea of this budgetary part of this mission, and of course, I know that it will be much lesser in comparison to any other mission. And secondly, the second question is related to the involvement and to the impact of the common mass, that we know that it is a very scientifically objected mission, and it is the first solar mission. I should mention these things, but what is the scope of just like the common people or the common college school students or the student community? Those are possibly our future researcher or scientist of our country can involve in this mission, or the outcomes of this mission, how they can relate themselves to the viability of this entire mission.
Yeah. And so the first part of your question, Sudipta, that the cost, as you correctly it, I mean, the cost of it is compared to any NASA mission, the cost is actually extremely low. And if you look at the cost of the ADITYA-L1 mission is around maybe 600 crore or some around that. And if you consider a mission like Parker Solar Probe or Solar Orbiter, the cost is much higher than that. So it's very, very cost effective. And I'll give you an example that if you, one of the reasons is that the innovation that is introduced into the system in terms of developing the technological system that people do at ISRO. That is one of the factors that cuts a lot of cost. And the second is that we plan the things in a slightly different way. For example, when you are sending the spacecraft to the L1 point, we are actually encircling the Earth for some time, and then using the gravity assist, the gravity of the Earth to actually have a slingshot towards the L1 point. Now, if you want to do the same maneuver through using, let us say, fuel, you have to have much more fuel or much more velocity requirement that in order to directly escape the Earth. So therefore, in terms of accommodating fuel in the spacecraft, and it will be much more. It will be much bigger. The spacecraft will be much bigger. It will be much heavier, and therefore the launch cost and associated maneuvering cost will increase. It's just a small example I'm giving. But the kind of trajectory that we are doing, we are using the gravity assist things in a much more efficient manner. We are encircling the Earth, attaining the velocity that is required to actually have a slingshot at the L1 orbit. And so those kind of small things are being incorporated. In addition to that, we are also different qualification processes that are there at ISRO. We are that also cuts the cost in a significant manner. It's much less compared to the NASA mission, and the NASA missions goes sometimes more than 1 billion in many cases. So if you look at the relative cost of 600 crore vis-a-vis more than 1 billion, it's much less at India. So to answer your first part of your question, it's ISRO's USP probably to have missions with a very small cost factor. And that's a great advantage. So that is your question. Yeah. And the second part is that your second question was you asked me that how it is the common person will get involved in this kind of mission. That's your question was, right?
Yes. Regarding the common mass or the common student, common researchers kind of thing, those are not directly involved in this mission.
Right. And it's a very good question, because you see, whatever we are doing at ISRO or by some institutes which are making the instruments, our eventual target is to reach out to the common masses. And I think one of the primary objective of ISRO is to make it societally relevant, and so that people get enthused to come into the science, do cutting edge science, and contribute to the not only to science but to the growth of the nation. Now, when ADITYA-L1 is launched, there was a very, very conscious attempt to reach out to university, colleges, where the MSc students are there, and workshops are being arranged continuously for the past 2.5 years. And we reach out to those colleges, those universities, those other than ISRO organizations to actually give talks, make them involved with the data analysis, and present in front of them, interact with them. And personally, I was involved in many such activities before the ADITYA-L1. Once I got involved with the ADITYA-L1 mission, and like me, many other people were involved. And so the idea is that when we call those MSc students, and in fact, at many times we also discuss this or talk to the school's children as well. So the idea is to enthuse them so much that they come to this field and use the data. And let me tell you that what ISRO wants to make this data available or make this science available. We want this data to be available to the common people of India. And the researchers, the budding scientists, they should use the data and as much as possible. And for that matter, if they want to interact with the scientists and the teams, we facilitate that. And we encourage them to join these exciting fields, and so that they can work and contribute not only to the science, but the growth of the space science and technology in India. And so therefore, this is a consistent effort that is being continued for quite a long time. And as far as ADITYA-L1 mission is there, I'm sure that this is happening for other missions as well. Yes, because this is the overall objective of us, that we want to involve people in this whole activity. It should be a movement of the whole nation. And therefore, when this data, when ADITYA-L1 goes and it becomes available to the public domain, we are already telling to people, please come and use the data, because we want to make it open data at some point of time, maybe very shortly. Once the data start coming, there is a lock-in period when the individual experimental team will evaluate the data and try to do their science for which they are toiling for the last 7-8 years. And then it's a very short period of time, maybe after a year or so, the data will be open to public. And anybody can write a proposal to ISRO. There is a system in place through website. They can write a proposal. In fact, they can operate the instruments the way they want. If their science is compelling, they can actually have a say on in what way they want these instruments to be operated. Not only that, this data belongs to them, and they can do the science. They can talk to the payload team. They can do their science on their own. And the eventual objective is to make this data available to everybody and support them in whatever way we can. So we want more and more university and institute people to come along and then join this particular activity. So this is a very good question. I wanted to convey thanks that you have asked this question. And we are doing this activity, ADITYA-L1 related, for last 2-3 years. We have gone to various places in India, east, west, north, south, and giving these lectures and workshops and telling them that please do come forward, please join this line, use the data. And in your institute also, I would encourage you to please get involved with your students and use the data as much as you can. And I'm telling you that there will be the data, huge data will be generated, and it will be open for all after a certain period. And so ISRO has a data repository, which is called ISSDC, which is at Bangalore. And all the mission data of ISRO is actually stored there. You can simply register and then get the data. And in addition, in ADITYA-L1, there will be a proposal submission system where you can actually submit a proposal by configuring the way that you want to operate the instrument. Okay, so depending on your kind of science that you want to do. So we are going to this level because it's an observatory class mission. If you ask for a time in a telescope, you actually define the way you operate. So it's exactly the same philosophy you are trying to follow. You can go one step further to actually define the configuration the way you want to operate, and then get the data. It's your, you can do it in your research, and the ISRO will facilitate that to make sure that your interests are safeguarded there. And so that is the policy that ISRO has taken. So it's a very golden time. We want people to join this field and then contribute. Yeah.
Absolutely. It is wonderful that this kind of prestigious mission can be directly connected with all the academicians who are involving in the space mission, because we strongly believe that this India very soon it will create a benchmark in the global basis, where the first of all is the low cost USP. This is becoming exorbitantly attractive for all the cases. Whenever even if I connect to anyone who is not even a scientist, or is a different set of scientists, they can, when they are hearing about that okay, this is the budget or this is the plan, so they are getting amused. So it is excellent. It is just in terms of excellence. I would like to request Professor Janardhan that if you want to make some comments on this mission, or if you want to mention anything or any comments regarding this, we'll be happy. Professor Janardhan, if you are still there.
Yeah, it is actually quite a journey we have had. This whole project began in 2008. At that time, when we started it, we had no idea how to propose a space payload, how much money to ask for. We had an idea of the science. Yeah, we want to do the following science. But in everything else, we were novices. And so the journey began from there. And we also didn't have a dedicated bunch of engineers working just for the mission. So, because PRL as an institute had only very few engineers, so we were actually taking engineers from different groups who worked for a few hours each day in the afternoon for us. And eventually they all developed, eventually after the project reached a certain stage, these people became part of the group, a part of an ASPEX team. But what I'd like to say is that these young bunch of engineers, the average age is of the order of 45 or so, they have done a remarkable job. As scientists, we can say we want the following thing. But to actually put it together and produce an instrument that meets all those specifications requires, our engineers have on average gone home every day only beyond 8, 9 o'clock in the evening. Not because anybody told them to do that. Because by very nature, I think these engineers, you give them a challenging task and it kind of gets into them. So for a small group of about 17, 18 people, it has been a remarkable learning experience. The kind of mistakes we made, the kind of, discussions we had. And it just, it also, like you can see, the people from other divisions also were involved in this. Many of the engineers, like I said, were from other PRL divisions. Deepu himself was in a different, initially he was not involved, but we kept in touch, we talked, we discussed, we published papers. So that was the journey. And I think 90% of the credit should go to the bunch of engineers who did such a marvelous job. Okay. And support from the institute, support from people at ISRO, at SAC, at Bangalore, the number of trips that were made by various people here and there. All of this was weaved into this story, to bring this thing out. And the pressure from, towards the end, the pressure from the ISRO side, the project director, you have to deliver this at this date. Why are you taking so long? No, you can't give excuses about pandemic and all that. So it was, all in all, it was a story that one can write a book on. And it was at times frustrating, at times enjoyable, but overall, I think it's been a roller coaster ride, but overall it's been positive. And we've come together as a group, and I would, given the experience that I have had, along with what I'm sure people will second me on that, I think this team of young engineers is perhaps the best in the country. Absolutely. In developing payloads, because they have the same bunch of people have contributed to Chandrayaan-1, Chandrayaan-2, Chandrayaan-3, ASTROSAT. So they have a huge amount of experience under their belt, a few people. And those few people have brought together the entire team to work as a cohesive unit. I think that has been the learning that we have had.
Thank you, Professor Janardhan. Finally, I'd like to request Professor Raju if you make a few comments, because we just after your comments, we will just ended up this interview.
Thank you. Am I audible?
Yes, sir. Yes, sir.
Yeah. So sorry, I'm on the road, so I could join. I'm able to join only through audio, not through video, because I'm not sure about the bandwidth. I hope it's okay.
Yeah, sure.
Yeah. I'll just try. I don't know how it looks like, but anyway, first of all, I would like to commend the team, Professor Chakrabarty, and the engineers. I would like to also second what Professor Janardhan just mentioned, and I would like to, in addition to that, what I would like to add is that, in fact, in addition to the engineers, I would also say Professor Dibyendu Chakrabarty himself, took on the mantle at a later stage, and that was it's a kind of non-linear things. Initially things develop in a gradual fashion, and at the later time, a lot of things pile up, and I think he has shown, Professor Chakrabarty has shown great character and maturity, and in kind of delivering the payload successfully after several of these reviews and several daunting deadlines. So I would I'm sure this would be the results would commensurate and more than commensurate the efforts that have been put in by these young people. I would like to consider Dipu also young, young scientists and engineers. So because and really, it's a commendable job. And as Jerry said, we are looking at the sun, which is an which with an intention that we would like to know the cause, and also in the future we are having missions to understand the effects of the space weather. So it would be a great combination that as a nation we have the data, our own data, which talks about the sources and of the space weather effects, and also the consequences in the ionosphere, thermosphere of those effects. So all in all, it's been I have been interacting with Deepu on various occasions, and I could see the tremendous workload, deadlines, and pressures he had. He has really, extremely, poisedly, he has taken out all those challenges. And of course, the team has been the engineers. As Jerry also said, I would also like to say that the engineers have really stood up to the deadlines. Again, the pandemic was a big speed breaker, so to say. And it's really a great journey. And when you look back, you can write a nice, you can tell stories, with a very, contented mode. But you take, you should imagine what was happening at the T minus, 2.5 years. One should place himself or herself in that position at that time, and that would be a different game altogether. It will be frustrating. It will be, nerve wrenching, and lack of appetite, lack of sleep, stomach upsets because you have to deliver the. So I think it's really. It's like it's a lot of things actually. So I commend the team, Deepu, and all the engineers, and of course Janardhan, who was there in the initial stages, and also all the PRL management and ISRO for all the support that's given, and then I really look forward to a great launch and a even greater science coming out of the ADITYA-L1 mission, and of course the ASPEX payload. And thank you for this opportunity. Thank you.
Yeah. May I just add one more comment? Yeah, I think before this recording even started, I had mentioned that Deepu took over the mantle of guiding this team in the most intense part of the preparations, when there were so many deadlines, and he's done a commendable job. And finally, I think when this whole mission succeeds, which I'm sure it will, it's a huge plus for India as a whole, as a nation. Because it's the first observatory class mission for solar science from India. And it will probably addresses more than what other missions have done from the L1 point.
Yeah. Thank you, Professor Raju. Thank you, Professor Janardhan. And of course, thank you, Deepuda and Professor Chakrabarty, for giving us this time and this discussion. I am quite confident that this ADITYA-L1 will open up a huge source for this research on the sun and sun-earth interaction. And of course, we are very proud for this entire mission and the first time, and we'll hope this will be a big success. And I from the Institute of Astronomy, Space and Earth Science. We sincerely thank you and congratulate you for building up this team, building up this mission. And moreover, we are quite happy and quite proud to have you as a member of our Research Advisory Committee. And we are confident that for after this mission or ongoing mission, we will have definitely having good suggestion, comments, ideas of making science out of it. So I again thank you, and I also thank my colleague, my senior and also a co-founder of IASES, Dr. Ankan Das. And sorry, Dipuda, if you possibly you want to say something, I am interrupting. Sorry.
Yeah, I just want to end it with a few sentences, if you allow me.
Please.
I didn't say what Jerry and Professor Janardhan and Professor Pallam Raju just said. I thank them for their kind words. And this interview will be incomplete if I, from my side, don't acknowledge or truly acknowledge the contribution of all these people, including Jerry is here and Raju is here, and our director who supported at every instant whenever I have approached him. Working with ISRO is a fascinating experience because you learn so many things. The condition is tough, and I think that's the time it brings out the best in you because you cannot goof around there. So whenever, in that process, I think I have learned a lot of things. Our team has learned a lot of things. Working with my team, as Jerry pointed out, is a learning experience because this is a team which I have not seen many teams, which Jerry is right, that were so self-motivated. They don't require any instruction. So my job, or as PI of this experiment, I don't have to tell them what is to be done at the next moment of time. They understand, and that's a great plus. You don't get such teams very often. And the help that we got from different ISRO centers, like Space Application Center at Ahmedabad, the UR Satellite Center at Bangalore, LEOS, other ISRO centers as well, the different review committees who took reviews, and I can take many names, but that's probably not needed here. But what I want to say that they kept on forcing us or transcending us those barriers, and that actually was, there are two ways to respond to it as a team, that once you succumb or you try to survive there, and so far we have survived. It's halfway through. I also want to remind myself that it is only the beginning because the spacecraft is yet to be launched. Okay, so it will go to ADITYA-L1, and the mandate with which we progressed, we started this whole activity, is the science part of it. Yeah. That is the biggest part that is still remaining. That itself is a lot of work, not only from the science, but to streamline the data part of it, how the data comes up, and then different levels of data are generated, how the calibration data goes into it. So all these things are taking our time now. And so I think that is one, this mission is far from over, and we would like to put the same intensity as we have put so far, just to make sure that the kind of confidence and the money, the support this country in general and this organization in particular is actually posing on our report, the trust it is posing on us. We do justice to that kind of trust and support. And it's a privilege to work in such prestigious project, and I myself feel privileged to have been a part of this project and to contribute in whatever capacity I can. And so that's all I want to say, because this interview will not be complete. I'm the face of ASPEX payload at present, but then if I don't say that what are the whole system has pitched in, and you are just seeing me here, so I must say that it's a system effort, and it's a fabulous system. And thank you for giving me this opportunity, Sudipto and Ankan. Yeah, thank you. It's a marvelous experience.
Thank you so much, Dipuda. It is actually our privilege to have you to know about this ADITYA-L1, and definitely our initial intention of this interview to make it more scientific in a simple way, to so that students, so that people can understand that what is going on. And of course, we fully agree with all the points, all the uh, points mentioned by the other two panelists on this in this meeting, that of course it is a huge teamwork, and we are quite happy that you are leading a team and making a very prestigious project in a successful manner. So on this note, I sincerely thank you for again giving your precious time to us. And obviously, there are some people who have joined for live listening, and we will make this video available for all the people who are interested to learn or know about the ADITYA-L1. So that's all from my end, and I request Dr. Das to make one ending comment and end this interview session.
Yeah, before Ankan takes over, maybe I would like to add one more point here, and I think it's important that people know about it, is that while it is going to L1 point, one part of our instrument will make measurement right from the 50,000 kilometer above the Earth to the L1 point. And so, as you know, there are two parts of our instrument, one for low energy and one for high energy. The low energy part is called STRIS and the high energy part is called STEPS. And STEPS will be made on the moment it is outside the radiation belt of the Earth. And so, this spacecraft will be having several rounds around the Earth. It's in an elliptical orbit, and then eventually it will be put into it will be injected into the L1, in a trans L1 orbit, basically, and it will take 4 months to reach there. Okay. Now, the STEPS instrument, which has 6 directional measurement, it will measure energetic particles from 20 keV to, let us say, 20 MeV. This instrument will be on as it is crossing magnetosphere, magnetopause, magnetosheath, bow shock, interplanetary medium, right up to the L1 point for 4 months. And this is the only instrument, only subsystem of ASPEX that will be operational during this phase. And this is a very important piece of information which I wanted to share with your audience, that we hope that this particular, and ISRO has kindly agreed to do that. It is slightly tricky to operate it at this phase, but they have agreed. And so we are very thrilled that right from probably 8 September onwards, we'll have this instrument getting started on and off in the Earth orbit, and then it will be continuously on as it is going towards the L1, crossing different layers of the magnetosphere like magnetopause, magnetosheath, bow shock, and then interplanetary medium. So that is a very, very unique kind of event that's going to happen, and we are eagerly looking forward to that. So I thought I will add that.
Absolutely, because just if you can say the proposed date of launching, and one satellite and one system is printing the data sheet of this starting from the upper magnetosphere height to the L1 point. So it is amazing. It is amazing from the point of view. So Dr. Das, if you add or something like that.
Yes, it's amazing to know all about it. So thank you, Professor Chakrabarty, for your time. And on behalf of Institute of Astronomy, Space and Earth Science, we really appreciate the opportunity to discuss and learn more about the ADITYA-L1 mission. And thank you again for your consideration. And we have spent almost 1 hour discussing this important mission, and wish all the success to the ADITYA-L1 mission. As of now, we are closing the session for today. But we would like to request Professor Chakrabarty if he could give us another interview after the successful launch of the ADITYA-L1 mission. Thank you.
Sure, it will be my privilege, and thank you very much for having me on your show. Thank you, and it's a great honor to have to serve you in your research advisory board. And I wish you all the success in your future endeavors. Thank you. Thank you for having me.
Thank you.
Yeah.